Hi, this is Team 1. In this video, we are going to present the proposal of our project entitled Fault Detection and Diagnosis of an Air Handling Unit of an HVAC System using Data-Driven Methods.
Building sector accounts for more than one-third of global energy consumption. That makes it one of the significant contributors to GHG emission. HVAC system consumes around 50 or 60% of building total energy consumption. So improper performance of HVAC and poor maintenance not only cause different faults, but also negatively affect the energy consumption, reliability, and efficiency of HVAC units, which result in thermal discomfort and poor indoor air quality. Therefore, adopting an intelligent strategy for fault detection and diagnosis can be a great way to identify the system malfunctions and ensure HVAC reliable operation. There are different FDD methods like model-based and data-driven, but HVAC unit is a complex system, so it's difficult to present an explicit and accurate mathematical model of the process. Therefore, automated FDD using data-driven methods can be easily implemented to predict HVAC malfunctions and faults for maintenance planning and self-heating in the next stage.
Now we will detect and diagnose the fault of an air handling unit with data-driven techniques as the main objective. Aiming to that, we have three goals. At first, important attributes will be found with two different methods. Pearson correlation helps us find the most correlated attributes. Moreover, embedded methods will find the most critical feature to train the model. This project will utilize random forest algorithms that builds decision trees on different samples. For the second goal, different classification methods will be implemented on the dataset. We will apply lazy learners, Gaussian and Naïve Bayes, and eagle learners, decision tree, random forest, SVM, and ANN to predict fault of the system. Finally, to evaluate different learners, we will measure and compare confusion matrix, accuracy, precision, recall, F1 score, and plot the ROC curve to prioritize different methods applied within the second objective. In the next step, more information about the case study will be described.
Our dataset is for a single zone constant air volume air handling unit, and the major components of the system are the supply air fan, the cooling and heating coils and control valves, the outdoor air, return air, and the exhaust air dampers as shown in this schematic diagram. The experimental dataset was generated by the Lawrence Berkeley National Laboratory, and the link of the dataset is provided in this slide. These operational parameters of the system constitute our dataset attributes. Also, this diagram shows that each data attribute is related to which part of the system. The dataset contains different kinds of faults from F1 to F14, which are listed in these tables. Also, this diagram shows the location of the faults, which are the outdoor air damper, the valve of the heating, and the cooling coils. With this understanding of the data, now we move to the exploratory data analysis.
Our main dataset has 21,600 rows with 16 columns or features. Fault detection ground truth column shows if the system is operating in faulty or unfaulty modes. Therefore, it can have the values of 0 or 1. However, in the metadata, it is mentioned that each type of fault has occurred in a certain period. Therefore, we added a new column named reason to show that what type of fault has occurred in each data point. Moreover, some features have incorrect data types and need to be corrected. After converting the mixed air temperature feature from object to float, we need to drop some missing values because there are 90 strings with values that are not null. Moreover, the distribution of faults over the dataset is shown in the following figure. Since our features are in different ranges, we need to scale them between 0 and 1 to have a better visualization. After scaling, we can see the parallel coordinates curves and the box plot for the scaled data. According to the box plot results, the outliers should be removed. In the following section, the preliminary results are presented.
In the preliminary results, in order to evaluate the significance of correlations among features, we used the Pearson correlation coefficients and showed the result in the heat map. We also summarized the attributes that have very strong correlation, like return air temperature and supply air temperature. For providing an insight into the model and also improving a predictive model, we use feature importance by random forest. We sorted our features based on their importances, and as you can see, the outdoor air temperature is the most important one. For the future work, we're going to adapting different classification method to train and test the model, calculating the evaluation criteria to validate each model, and also comparing different apply methods to find the best method for FDD. Here is our references, and thank you for your time.